Here is the 20th video showing right there. That is number 20. And that is, and that is probably number 20 for him too. Okay, I'm not counting, but I'm totally counting. The video killed the radio star and video saved the Zoom stars in this class. Okay, no, but thank you guys. Totally appreciated. Totally no. So hello. That's my long way of saying hello. Ah, good afternoon. Okay. Wait, lots of hellos here. Okay. I see you. I see you. So wait, right. So I'm saying hello to Lila and Raymond and Mike because I see their videos. I'm saying hello to Jerry. Yes, hello, hello. And I see the hand wave. Thank you. Um, and and I hope that they are getting the points that they, all right, I'm going to stop talking about that. But I see the avatar, Jerry, and I appreciate it. And wait, there's more people in the waiting room. And there's a bunch of people in the chat. So I'm going to say quickly hello to the people in the chat. Also, why this? And we'll get rolling, obviously. But yes, hello, because it's been a long time. Yes, it's been a long time. So hello, good afternoon, Luis. Hello, Samea. Good afternoon, Montserrat. Hello, Sophia. Good afternoon, Jadith. Good afternoon, Raymond. And yes, I will report on it. Thank you for your inquiry on my well-being. Yes, it's getting a little rocky, but it's fine. Thank you. Hello, Jerry. Good afternoon, Camille. Good afternoon. Good afternoon, Leah. Wait, no, why I doing it wrong again? Oh my God, see, it's been that long. No, it's Leah. Wait, it's Leah. It is Leah. Tell me again. Oh my God, I do this every time. All right, anyway, but good afternoon. And good afternoon, Danielle. Um, wait, Leah, is it? Oh, there's more people. There's Nico. All right, all right, all right. Wait, Leah, I'm so sorry. Leah, I think it is Leah, but is it Leah or is it Leah? Tell me, Leah. Wait. And hello, Nico. Okay, I'll just let it go. Oh, and hello, Joyce and Mancha. I didn't see you. Hello, hello. Awesome, awesome. Thank you for showing video. And again, those of you, I hope you're submitting for, I think most of you are, but those of you who keep showing video, remember you can submit for points in the video portal. I think most of you know, but you can submit more than once, as many of you clearly do know. You know, like Joyce and Mancha, you show video a lot. Like just I hope, and you should get a lot of points for that. I just want to make clear that I know that, and I hope you know that. But okay, okay. Now, who else? And hello, Nico. Okay, we have to get back to physics today, yeah, of course. But first, I'm going to put a bunch of things in the chat right now, because I talk so much. So I'm going to put a big thing in the chat, and I'll probably repost it a couple of times as more people come in. So forgive me. This is just to save me time talking. So hold on a second. A couple of things in the chat. Number one. Ay, ay, ay. Oh, hold on. The chat thing is too long, apparently. Um, okay. One thing, there's something in the chat. Just look right now. It's just to acknowledge that I mean, this is partly an answer to Raymond's question too. Like, so things are getting a little harder on my end. Now, I don't mean that as an excuse, but it is becoming a little bit more challenging for me to get things done. So I have not forgotten about your exams. And the bottom line is you will get them back in time to make improve, to be prepared for your final exam. Okay. I understand, to ease anxieties about your performance in the class. I don't want to create more anxiety. It is making me anxious that I haven't given them back to you yet. So just read in the chat. You're going to get them. They are starting to come back now. It's taking me too long, but they are happening. You will know what you need to do before you take a final exam. And again, the bottom line, so please just bear with me and forgive me. Like it's not that they are forgotten, and it's not that I don't think no, okay, thank you. No, I appreciate it. And I'm not trying to whatever. I put in the chat so I wouldn't take too much time to talk about this again, but I just do want you all to know it's not like they're missing or forgotten or something. And I know it matters for a thousand reasons. But the other thing is, again, just to reassure you, if if at any moment any one of you just text me at my phone number, my cell number, and we'll make a quick appointment to talk on the phone so that I can like sit with you with your individual facts, whatever I have, even if I still don't have all of your facts, like even, you know, I owe you more information than you owe me in many cases. But even if it's good to just sit, and it has, some people have taken me up on this already, just to sit down and for me to hear your voice and you to hear my voice, and just to hear this is what I think the situation is right now. This is where you're trending, you know, or this is your general thing that you need to work on. Like I can do that with any one of you if it helps at all. Just again, know that if you are still with me at this moment, if you're still in the class paying attention to me and trying to do your best, then your academic situation in this class is probably better than what you think, if that makes sense. Probably. I mean, probably. Um, so if it can help until I can get your score back to you and your feedback back to you, if you if it can help, just text me. We'll make a moment to talk and we'll clear the air. Okay, so that's one thing. Thank you for bearing with me on that. Wait, I seem to have lost the screen. But now the other thing, if that makes sense, if you forgive me for the moment, the other thing is that somebody asked me in the other section or in one of the other sections about the final exam. Now, of course, I'm just as awkward to talk about final exam right now as you might. It might be just as awkward for me as for you to talk about it if you haven't even gotten your midterm back yet. I get that. However, you want to plan and you deserve to plan. So let me be clear about the final exam right now. Again, you will have your midterm feedback before you do a final. Please understand that. But and also, please understand that the final exam will be the same format, the same expectations as the midterm, um, you know, take home and open universe and all that, you know, for good or for bad. But that said, you should still know, you know, like when it's due. So I'm going to put in the chat right now a second announcement. I'm just going to make this clear. Well, all right. First of all, ugh, hold on. Just for anybody who, all right, for anybody who just joined or whose Wi-Fi is, so I just reposted the same announcement I just did a second ago. Oh, I don't know. Huh. Bang, bang. Okay, sorry, I'm looking at your chat. I don't even know what some of these symbols mean. Okay, I'm so old. Okay. Um, um, but thank you. I think, I think. No, I appreciate it. But now, all right. So I just reposted the same announcement just in case anybody just joined or had a Wi-Fi issue. But now, so just look, if you, it's the same thing if you already saw it. But now, announcement number two that's relevant to everybody about the final, just to be clear, yep, that is this. Bear with me for a second. You can tell I really am. Yeah, here we go. Okay. Announcement number two. Oh, come on. Yeah. Announcement number two in the chat. And I will put this in Google Classroom as well. I just like to have these things written for you, you know, so you can copy and paste it or be clear in your mind or in your calendar, or whatever. The way the final exam will work, say it will work the same way, but as far as timing, um, like you know, I looked at the John Jay official calendar, and in the official calendar, your final exam, I believe, is supposed to be like on Monday of the final exam period. I believe it's Monday, December 16th. I might be wrong. It might be Wednesday, but I think it's Monday, December 16th. So, and of course, they make that schedule to try to be as fair as possible to so you don't have a million exams on one day and all that. So I don't want to mess with that. But the thing is that your exam is take home, right? You're not going to come in and sit for an exam for me. Therefore, if it's good for your planning or your distribution of time, if you want to take my final exam during the period on Monday when it's posted in the John Jay schedule that you're supposed to take a physics exam, by all means do it. That's fine with me. But that's on your time. You don't have to do that. I am saying because I want all students to be able to work together and all the sections to have equal access. Therefore, your exam will be due midnight Wednesday, uh, the 18th of December. Um, and it will be posted prior to that. It'll be posted no later than Friday of the week before, possibly Thursday. I'll give you those details in Google Classroom. But so again, you'll have the full weekend and the Monday and Tuesday to work on it with each other and stuff if you wish. But if you don't like doing things that way and you just want to like sit down and do it, then you can do it during the whatever period, John Jay says that you can. I hope that's clear. But it'll be due midnight Wednesday, December 18th. Just do me a favor before we move on right now. Uh, Raise your hand if that's clear. If the final exam, okay, thank you, Lila. Okay, thank you, Raymond. Thank you, Nico. Thank you, Mancha. Thank you, Danielle. Thank you, Joyce. Thank you, Samaya. Thank you, Montserrat. Thank you, Camille. It's set. All right, great. And there's others. I just can't see because of it. Thank you, Jadith, Luis, Sophia. Okay, great. So again, if there's ever any issues, text me. Just please also know the bottom line with the whole thing. I hope this is clear at this point. I'm human, you're human. I'm imperfect, you're imperfect. The bottom line is the benefit of the doubt goes to you. If you're still with me, if you're still hearing me, if you're still trying your best, then if you're on a borderline of some situation or there's some ambivalence or something like that, believe me, the benefit of the borderline or whatever will go to you. My interest is in you doing well as possible. Or another way to put that is if you're trying to interpret a grading policy of mine, and you're trying to figure out why something is complicated, assume that the reason is because I believe that it'll lead to your highest possible grade in the situation. Like again, that's the bottom line. Whatever. Okay, so let's move on. If there's no question, so when in doubt, reach out to me and ask me. Okay, so let's move on with physics. Uh, what I want to get back to now, in physics, is the stuff on the board right here. Um, what I want to talk about today is electrostatic flux. Technically, there was a homework due about this that I just realized was technically due today. If you did it at all, I think I owe you a ton of points. If you tried it at all, you can get all the points if you tried it at all on time. If you didn't try it yet, you can still get most of the points. And everything I'm going to start saying today and Wednesday this week will help you a lot with it. It's hard. It's not easy, but it's a great time. It's a very important topic in physics, one of my favorites. So here's the deal. So the topic is flux. Okay. Now I'm going to define flux right now in a number of ways. I'm going to define it mathematically, and I'm going to try to explain it physically. It's an abstract concept, but it's a very important concept. One thing is the way I'm going to try to talk about flux, all the ways I'm going to try to talk about flux, they all rely on an understanding or at least some sort of like exposure or appreciation to electrostatic field lines. So when last we met, which was a long time ago, I was trying to elaborate on or expand on the notion of these field lines. And in principle, you had watched the two videos about electric field lines. Now, I still think it's really important. If you haven't watched those required videos about electrostatic field lines, please go back and do so. If you did and they didn't mean anything to you, then watch the video from last week where I sort of tried to elaborate, and maybe that will help you go back and see the basics from those two videos. But you got to have some kind of recognition of what electrostatic field lines are in order to understand flux. The summary, so I don't want to rabbit hole here. The summary of electrostatic field lines is that field lines are composed from field vectors. They try to capture the same information as field vectors, but they do it in a different way. The ultimate thing is that field vectors are straight arrows, right? I'm intentionally not writing this down because I want to, but if you write this down and you screenshot it and submit in the notes portal, great, you'll get points for that. I'm saying a field vector is an arrow whose length indicates field strength, field magnitude, and whose orientation indicates field direction. A field line is not an arrow. I mean, it has arrowheads, but a field line is not a straight line. Is a curved, continuous line. Field lines can go on forever. They can bend and twist. Field lines are smooth. That is to say, if you have a picture of a bunch of field vectors in the picture, and the bunch of field vectors indicate what the field magnitude and direction is doing at every single point in space due to some source, then if you sew up all those field vectors, if you attach them all and turn them into lines, curved, smooth, simple as possible, symmetric lines, then you get this thing that we call the field line diagram. So field lines are also meant to indicate magnitude and direction of field at any point in space. The distinction is that, and again, this is just technically review of what we said last week or what the other video said, but when you look at a field line picture, the orientation of any field line at any given location, the orientation of any field line indicates the field direction at that location. And the density of field lines at any given location indicates magnitude of field at that location, right? I'm going to say it one more time, then I'm going to move on. Again, I'm intentionally not writing it down because I want to like move on, but I want it to be clear where we are in the material. A field line diagram has a bunch of lines in it that start at positive or come in from infinity and land on negative or go out to infinity. They don't stop. Field lines don't stop at random points in space or therefore at random points on the page, on the piece of paper. They only will stop at negatives or start at positives. And what field lines represent is the sum of all field vectors. So the way when you look at a page and you see a bunch of field lines somewhere on the page, where the field lines are going is where the field is pushing or pulling. But how close together the lines are is how strong the field is. That's what I'm saying. And I'll say it one last time. How close the lines are together is how strong the field is. How close the lines are together on the page is how strong the field is in the point in space represented by that page. Okay? So length of line no longer means anything when you're talking about field lines. Density of lines means strength. And last thing about that, when I'm saying density of field lines equals or represents magnitude of field strength, I don't just mean it in a rough qualitative way. I mean, and this is why I had to go into so much detail in the other videos, I mean, if you actually follow all the rules of drawing a field line diagram, or you use a computer program application to follow all the rules of drawing a field line diagram, then one of those rules is that you actually pick a scaling factor such that for each coulomb of source charge, we're drawing, say, 8 field lines or something like that. And then if you stay consistent with that scaling factor that you chose, then it means in the long run that we're not just roughly saying that density of lines kind of suggests strength of field. We're saying, like, literally, if you drew a good, or if a computer generated a proper field line diagram, then you could literally count field lines and literally precisely infer or calculate the strength of field in like newtons per coulomb. So field line diagrams are like graphs or vector diagrams or free body diagrams or anything else in physics. Like they're literally a quantitative calculational tool when used, when written and read correctly for what it's worth. So field lines are important, okay? And they're the way we imagine the world. Bottom line, when we imagine field line picture, the closer the lines are that we're seeing, the more we're imagining that field strength is high. And that means that the force waiting to happen at a point in space is high, okay? So what does all that have to do with flux? Flux, okay. Okay, I'm going to say a lot here. Okay. Okay. I'm saying I want to talk about flux now, right? And I'm talking about mathematically. Now. I'm going to get mathy now. Everybody watch out. I'm going to get mathy. Um, First of all, notice I'm using these little triangles. Okay. Well, wait, let me back all the way up. I'm going to say in really general terms, first, in really general, broad, oversimplified terms, just to give you a picture, what electrostatic flux means is electrostatic field times area. I'm going to say that again. Like in broad, oversimplified terms, just so you can get an intuitive picture first, flux in general means stuff times an area. Electrostatic flux means electrostatic field times area. And now I have to be much more specific about that in a minute. But in general terms, to talk about the electrostatic flux through some area, some surface, some two-dimensional region of space is to talk about the electric field strength through that space, through that area, times the amount of that area, times in simple terms. I'm going to go one step further. In fact, let me go one step further, just for, again, for intuitive terms. Oh, God, why does that happen? I know why it happens. So first, there are a lot of mathematical nuances here, okay? But before I get into the mathematical nuances, just in broad terms, what I want you to know is flux means field times area, field times area. So it's not a dense, it's not divide, it's times. Field is measured in newtons per coulomb, right? Field is like force per charge, and area is like meters squared or square meters, or whatever, right? So in broad intuitive terms, if I have some area and there's a field going through that area, like a bunch of electric field lines busting through some slab, some bunch of square centimeters or something, or square meters in space. The stronger the field going through that area, the more we would say there's flux. And or the bigger the area, the more we would say there's flux. If either one is bigger or both is bigger, the flux is bigger. Okay, so it's not a quotient. It's not like you understand what I'm saying? It's a product. So more field lines in an area means more flux. More area with field lines means more flux. That's in broad terms. Now, what that doesn't tell you is why you would care. I'll get to why you care soon, but that's what it is in broad terms. However, there are nuances. First of all, you will notice back on this page, what I'm really talking about first right now is a small but finite amount of flux. Like I'm triple equal signing what it would mean to be a small but finite amount of flux. A small but finite amount of flux would be electric field magnitude, excuse me, would be electric field vector dotted with small but finite surface vector, or small but finite amount of surface or area. So S stands for surface or area. I'm using the two terms interchangeably for the moment. So there's two things I have to like elaborate on here. Okay. So two things. I'm trying to say that right now I'm talking about a small but finite surface being multiplied by an E field and thereby yielding a small but finite amount of flux. So I need to elaborate why am I making a big deal of small and how small is small? That's number one. And number two is I'm ultimately saying that field is a vector and I'm ultimately saying that surface, bizarrely, can be treated as a vector and that we're multiplying these two vectors in a manner that we call the dot product and which actually was discussed in your homework number two, which we never really talked much about in class, but now we finally are going to. Um, so what is that? What's going on with that is the second issue. Okay, so first issue first. And I may have mentioned something about this before. First issue first. Whenever Well, maybe I actually in this class I may have mentioned this. Forgive me if I've already written this down for you, but quick review. Okay. Okay. Remember, if I've said this, for any variable, call it z. When we talk about delta z, we mean a small but finite difference between two values of the variable z. Like the different, as in when we call it y, when the variable's y, delta y is rise, like y2 minus y1, and delta x is run, x2 minus x1, right? You remember this from calculus. And notice when we do that, or in trigonometry, pre-calculus, like when we talk about delta y or delta x, the whole idea is, yeah, it's just that delta y or delta x or delta z means x2 minus x1 or y2 minus y1 or z2 minus z1. It means that even though the difference might be really small, like you might have this big curve on a big graph and you're zooming into this tiny interval on the big graph, still, even though it's really small, it's still measurable. There's still a distinction between Z1 and Z2. They're separated by enough of a number that you can literally subtract one from the other and get a difference that you call rise or run or whatever. And so delta is what we use when the difference, even though it's small, is finite. When we switch to dz or d whatever, we're going to the limit as the difference between the two values of the variable get arbitrarily close to zero, right? We switch from delta to d when we're going from difference to infinitely small difference, which we call differential. You remember this from earlier in the course, I think. I mean, when we got into differential equations and all that. So right now, so when I say deltas, when I use a delta, I'm trying to connote a finite, like we're not into calculus yet, in other words, yet. When I use delta, I'm talking about a finite chunk that is finite, measurable, deal mentally manageable, uh, but small. What do I mean by small? I think we've mentioned this before when we were talking about work, or maybe we didn't. Well, anyway, how small is small? Okay, what I'm saying here, I'm now going to transition from the general math to the specific physics. When I use delta, usually what I'm trying to emphasize is that I've got a quantity or an interval that is finite, but is small enough to prevent change in the other variable. And there's always two variables, right? A dependent and an independent. I mean, there's always at least two variables, dependent and independent. So here in this context, when I'm talking about flux, what I want to say is right now, well, tell me if you want me to go back. So what I wrote here is we use delta in one variable when we mean small enough to prevent measurable variation in the other variable. That's what I mean in general in math. If I use a delta, like rather than a d. Okay, so specifically in physics, what I'm talking about here, and again, please tell me if you need me to go back. It's fine. But okay, so right now, I'm saying I'm deliberately, and this is what we do a lot in physics. Like this is like a thing. And technically, we did it back when we defined work, but I don't know if we really discussed it this way then. But again, big picture here. I'm trying to define flux for you. I'm trying to give you a mathematical and physical picture of electrostatic flux. But the way I'm doing it is by a technique that we often do in physics. I'm first defining what flux is in the small case. And once we get it straight in the small case, then I'm going to blow up or extrapolate or expand and see how I have to tweak my definition to allow it to apply more generally in big cases. So what I'm saying right here is I could tell you what flux is in the small case. In the small case, flux is field times area. What do I mean by the small case? I mean the case of small areas. What do I mean by a small area? I mean an area that's so small that the field doesn't have time or space to change throughout that area. So really what I'm saying is I can define flux for you as long as the situation right now, I can define flux for you in a situation where flux is easy to picture, or comparatively easy to picture. Flux is you have an area, you got a bunch of field lines, so you got like a density of field lines going through the area. Assume that the density of field lines is one number. Like assume that the field lines are like all parallel with each other. They're not doing anything weird. There's just a bunch of field lines going through an area. And let me even back up further because I know field is still new to many of us. Like I'm saying, say there's like a proton over here, or there's a bunch of protons over here, or maybe there's even like a plate of protons, or say something over here is creating field. So there's a bunch of field lines coming out of that source. So then I go to some other region of space and I'm looking to make to figure out what the field is doing at some other region of space. So what I'm saying now, if I were to take a slab of space, I know this is very abstract. It is very abstract. I'll do examples soon, but I've just got to lay out the fundamentals here. If I picture a slab of space, like a cross section of space somewhere, like a rectangle or a square or a triangle or a disc, just some kind of area of space, a two-dimensional region of space, and I picture all the field lines busting through that region of space, if the number of field lines through that area, the density of field lines through that area represents the strength of the field. If I take the strength of the field and multiply it by the area, I get a number that is called flux. That's what flux, just like work is force times displacement, flux is field times area. I haven't exactly explained why we would care yet. suspend that for a minute. Just stay with me as to what it is we're caring about. What we're caring about is strength of field through an area times an area. That's what I'm saying is flux. And right now, what I'm saying is, well, that's a manageable definition. That's a manageable calculation, as long as the area you're looking at is small enough that the field lines are doing the same thing throughout the area. If there's just like a bunch of lines going through there and they're all sort of parallel, so they all have the same density, they're not in some funny pattern or not some changing pattern, then you would just count up the number of lines per area, you know, um, and that would be the density of field lines. That would be the strength of the field. And you'd multiply that one number by the area. That would be flux. So that, stop me. Wait, I'm just going to, okay. So I'm saying right now, if flux is field times area, that's a totally workable, doable thing, as long as you have one number for the field. How can you, otherwise, I don't know what number to plug in for field or what vector to plug in for field. How can I ensure that I have one vector, or excuse me, one vector quantity to plug in for the field? I can ensure that as long as my area is small enough that nothing wackily changed with the field throughout their area. So that's why I'm restricting myself for just this moment to small surfaces. And I'm saying a small but finite amount of flux is defined to be a field strength times a small but finite amount of area. I'm going to pause for a second. That's the first issue. That's why I'm using triangles. That's why I'm talking about small, small, small. Of course, I'm going to expand that soon. But before I move on to the second issue, please raise your electron again if you're like cool with me to go on. Like, does this make sense? Are you okay with this for me to move on? Thank you. That was fast. I love this class. It's so fast. I don't see all the names, but I see the numbers because I'm in the strange. Thank you. I see at least 6 hands just went up. Thank you. All right. That's good enough for me. Totally And again, if you did that, if you just put your hand up, you can totally submit in the portal that says, please go forward, right? By putting up your hand, you just told me to move on, which is helpful. And of course, I'm not moving on. I'm just talking about it. But submit for points. You deserve the points for doing that. But okay. So I'm moving on now to the second issue. The second issue, which is a little bit more, maybe a little bit more nuanced, well, whatever. The second issue is, let me see what color I used for these issues. I think I used yellow. Okay. Second issue. Okay. So now, okay. So now I want to get into this vector multiplication thing. Now, again, this was explained and worked through in your homework too, but so you looked at this in a sheet. What I'm about to say, you sort of looked at aspects of this in a sheet and you sort of practiced it, but you didn't know why, and you didn't really get a discussion or feedback on it. So here it is now, for good or for bad. The fact is, so I'm being mathy again now. So forgive me, I'm going to get into like the mathematical concept here of multiplying vectors. Um, uh, like in general. And then, of course, I'm going to apply it to this concept of flux. Okay, first, just to make this clear, again, this was in homework too, which, by the way, if anything I say right now helps you at all to go back and improve your homework too, by all means do it, and get more points, whatever. What I'm saying right now is when vectors are involved at all in any mathematical or physics context, there's three different ways that multiplication can occur. The first way is you could take a vector and you can multiply it by a scalar. We do it all the time, even when we're not realizing that's what we're doing. When you multiply a vector by a scalar, you necessarily always get a vector automatically because a vector, and that's, I'm just saying this for education's sake. Like, it's in fact how we construct vectors in general. If you have a vector is an arrow with magnitude and direction. If you multiply it by a pure number, all you're doing is taking an arrow and enlarging it or shrinking it by the amount of that pure number, like literally, right? Like 4 miles displacement to the northeast. If you multiply it by 3, you're saying that you now have 12 miles to the northeast, right? Like if you walk 3 times as far. So when you take a vector and multiply it by a scalar, you're literally taking an arrow and you're just scaling it up or you're scaling it down. The result is an arrow of the same direction, but a different size. That's honestly why we call pure magnitudes scalar quantities, because they just scale pre-existing vectors. I hope that makes sense. So when you multiply a vector by a scalar, you always get a vector. End of story. And we do that all the time. Anytime we construct a new vector from an old one. Well, we do it all the time. But now, more interesting in a way, or more nuanced, is if you have two vectors, two pre-existing vectors of arbitrary length and arbitrary direction. If you have two vectors, there's two different ways that you can multiply the vectors, as homework 2 delineated. You have a choice. You can either multiply the two vectors in a manner that will produce a scalar quantity, or you can multiply the two vectors in a manner that will produce a vector quantity. The first approach is called dotting the vectors. It's signified by a dot. The second is called crossing the vectors, and it's signified by an X. Now, both are possible at any time with vectors, and both are very important in physics. The, the one that we're concerned about here right now with flux is the dot product. So I'm going to, so I'm going to elaborate on that right now. Wait, oh, yes, absolutely. Sorry, yes. Hold on. Just let me know when. No, I love that. And that counts for points for please go back, as you know. So just let me know when you. Sorry. Oh, great. Okay, thank you. Okay, okay, okay. Thank you. As usual, the most important thing I'm saying gets squashed at the bottom. Hold on 1 second. Let me just read this out loud, and then I'm going to, obviously do an example in a second or whatever. Um, Let me read this out loud so you can get it. It says the scalar or dot product between two vectors measures the extent to which the two vectors line up on the same axis, the extent to which they line up on the same axis. That is, the dot product, the scalar product, measures the extent to which the two vectors could be treated as pure numbers on a number line. So I'm going to show you this mathematically, but what I'm trying to say in English is when you're trying to multiply vectors in a manner that gets rid of their directions, if you're trying to multiply two vectors in a manner that would produce a pure scalar quantity, what you're trying to do is only multiply the the matching components of these vectors. When you multiply two vectors in a scalar fashion, you're actually asking, okay, you're not, well, you'll see in a minute, but you're asking how much of this one vector lies along the other vector. I'm not going to multiply the whole vector length by the other whole vector length. I'm going to multiply the length of this vector, the length of the component of this vector that's actually parallel with the other one. Because if you're trying to get a scalar product between the two vectors, what you're really asking is, to what extent can I get away with treating these two arrows as though they were two arrows on one and the same number line? To what extent can I treat them like pure numbers? Well, you could treat vectors like pure numbers as long as they were parallel with each other. If they literally were not differing with regard to direction. So in short, what I'm saying is this. Okay. Just assuming, oh wait, something's in the chat. Wait, sorry, something's in the chat. Or did I? Oh, yes, absolutely. Sorry. Yes, absolutely. In fact, I'm gonna get a tissue while you tell me when. Yes. Okay, and so let me know. So thank you, Nico and Abdu. That you got it. Okay, great, great. Okay, so what I'm saying this is in general now. Again, this is math. It's just like it doesn't. We have 20 minutes. Okay. Um, say you have two arbitrary vectors, A and B, and say a couple of things. Say number one, just notice my notation. I'm just trying to be clear about notation. When I draw a letter with the arrow above it, I mean the full vector quantity, the magnitude and the direction. If we're in a vector context and I drop the arrow, it doesn't mean that I've forgotten it or it's a typo. I mean, it might mean that, but if I'm being deliberate, it doesn't mean it's a typo. It means when I write the A without the arrow, it means the pure magnitude of the vector A. It means the size without the direction of the vector A, right? So if I use that notation that I'm trying to say here, and if I take these two arbitrary vectors and I put them tail to tail, so I'm not adding them. I'm just like trying to represent them. My God, someone's already put the please go. Oh, please go forward. Wait. Oh, should I go? Oh, okay. Okay. Sorry. I'm getting this. Okay. Um, I know who you are. I know who you are. I'm paying attention to everything. Just not responding fast properly. If theta is the acute angle between the tails of the vectors, so I'm just drawing them so I can see, oh, this is how they differ in direction. Theta is just how the two vectors is the simplest way to represent their difference in direction, right? Given all that notation, then Okay. What I'm saying right now, and of course I'm going to do an example. Well, sort of. I'm going to apply this to the physics in a minute. I'm not really going to do an example, but I'm going to apply it to the physics. What I'm first of all saying is the I am saying here explicitly as a definition from now on, the dot product between two vectors is the length of one vector times the length of the other vector times the cosine of the angle between them. The cosine, specifically the cosine of the angle between them. Why? Well, why the cosine? And by the way, this is what I'm talking about now. We're focusing on is the dot product, just so that you see the whole picture. This is in contrast to the cross product, which we need for other contexts in physics. The magnitude of the cross product is the magnitude of one times the magnitude of the other times the sine of the angle between them. Like why? Like what's going on here? The dot product always relies on the cosine of the angle between because sine super cosine crappy or sine super cosine confusing or sine super cosine counterintuitive if you like. What I mean is the sine of zero is zero. And the sine of an angle gets bigger as the sine of an angle gets bigger as the angle gets bigger, right? Like that's the thing that sort of makes sense to people that's what you would invent if you were on a desert island inventing trigonometric functions. The cosine is backwards of that, right? The cosine of zero is one. And you should memorize. If you're going to memorize anything, just remember sine of zero is zero, and everything else is like follows from that. The cosine of zero is one. As an angle gets bigger and bigger, the cosine gets smaller and smaller, all the way to the point where if the angle is 90 degrees, then the cosine is zero. Now, when you first learn that, it's like the opposite of sine and it's confusing. Like, well, maybe it was to me. Like sine, I understood. Cosine seemed crazy to me. Like, why did we need that? Well, here's an example of where you need that or where it's good. Because if you really think about it that way, what cosine is measuring really is parallelism. Remember, cosines and sines are always just decimals or fractions between 0 and 1, right? So if you look at two vectors, any two vectors, did I draw them? Yeah, like vector A and B. Here's A and B. If I want the dot product of A and B, what I'm saying is I'm going to take the length of A, I'm going to multiply it by the length of B, but then I'm going to multiply that by the cosine of the angle between them. By multiplying by the cosine of the angle between them, I'm multiplying their seeming numerical product. I'm multiplying it by like a scaling factor, sort of, a percentage from 0 to 1, right? I mean, a decimal, which is like a percentage, between 0 and 1. That percentage will get higher and higher as the angle gets closer and closer to 0, as the two vectors get closer and closer to each other. So dot products measure parallelism all the way. Look at the extreme cases. If the two vectors were purely parallel, if the angle between them were 0, then I would take the length of one and the length of the other, multiply them, and then I multiply by the cosine of 0, which is 1. So I would just get their pure arithmetic product. Right? So if it was a vector of length 3 on top of a vector of length 2, it'd be 3 times 2 times 1. I get 6. It would just be like multiplying two numbers, 3 and 2, on the number line. However, in contrast, on the other side, if the two vectors were purely perpendicular, it means they have nothing to do with each other physically. Because remember, Galileo's principle, like the laws of physics, take place and are true in each coordinate system independently. yet simultaneously. So whatever's going on here doesn't affect what's going on here in the world of space and time. So if I have two vectors that are purely perpendicular, no matter how big they are, if I did their dot product, I would do the length of one times the length of the other times the cosine of the angle between them. The angle between them would be 90 degrees. Cosine of 90 is 0. So the dot product would be nothing. So the dot product and everything in between, like the closer to parallel, the higher percentage of the dot product gets returned. So the dot product is like measuring how big are these two vectors, but not only that, how parallel are they? The more parallel they are, the more we will take into account their size. Last thing I'm going to put in, then obviously I have to move on. I'm looking at the time. Oh, I really have to move on. Okay. Last way to put it is, I mean, multiplication is commutative. So when you multiply one vector by another, when you multiply one length, like the length of A times the length of the vector V, but then you multiply by the cosine of the angle between them, what are you really doing? You're in effect, you're saying A cosine theta times B. I'm saying AB cosine theta is the same thing as A cosine theta times B. So a different, more helpful way to look at this, perhaps, is that when we throw in the cosine component, what we're really asking is how much of we're not multiplying one whole vector by another vector. We're multiplying the component of the first vector that is parallel to the second vector. That's all we care about is the pieces of the two vectors that are lined up with each other. That's what we do when we get, and we're doing all that because we don't want a vector answer. We want a pure numerical answer. So we're trying to get rid of directional deviations when we do the scalar dot product. Okay, that's what the scalar product is. That's what the dot product. Now, how does this relate to flux? Okay, I'm just going to read this. I'm watching the time, 10 minutes. I'm going to read this. And I'm going to go to the next page. So, how this relates to flux. Flux is E field vector times area vector. But what's an area vector? How does area have a vector? Well, in physics, we care about the orientation of areas in order to track. So, like area itself is not a vector. Area is a two-dimensional quantity, region of space. But what we do whenever we're looking at a bit of area in physics, in our minds, we attach a normal vector to the area. We attach an arrow sticking out of the area. Normal in physics means perpendicular, right? So we attach, normal means perpendicular. So we attach always, when we're dealing with areas in physics, whenever the orientation of the area matters, we attach a vector to the area in our mind, and the vector sticks out of the area at a 90-degree angle to the area. So, like this. So, tell me if you need me to go back. But, oh, sorry. What I'm saying is, okay, I'm saying from now on, with 7 minutes left, when you have an area of any kind, or even here, let's even a small area, delta S, we imagine an arrow sticking out of that area. The length of the arrow is S, about 15 square meters or 20 square meters or whatever. And the direction of the arrow is out of the area, perpendicular to the area. The purpose of this is therefore if the area starts, whatever direction the area is, we can track the orientation of the area by the orientation of this arrow. Because, of course, if the area moves, rotates, the arrow will rotate by the same amount, right? So, and again, tell me if you need me to go back. I know we have 6 minutes. Okay, this is, like I said, it's a little nuanced. On the one hand, so bear with me here with 5 minutes. On the one hand, I'm saying, so first of all, what I just said is here's how we're turning area into a vector. We're sticking a vector on it that tracks the orientation of the area. Like, okay, then I'm saying, okay, so now we can apply dot products because area is a vector and field is a vector. So we can multiply them by whatever means we want. And if we're going to multiply them in a way to get this thing called flux, and if we want flux to be a scalar pure quantity, then we're going to do the dot product between these two vectors. Now, the odd thing that you have to track here for 4 minutes is I just, I'm not contradicting myself, but this is confusing. Bear with me. The dot product measures parallelism between two vectors. It measures, so the dot product between an E vector and a delta S vector is the magnitude of the E vector times the magnitude of the delta S vector times the cosine of the angle between them. So when we do flux, we're not just caring about magnitudes, we're caring about directions. We're looking at how parallel the an E field line is with an area vector. The odd thing is, I just said that the E field vector is drawn perpendicularly to the area. That's the way it is for reasons that are traditional and help in lots of other contexts that I'm not going to get into right now. But therefore, what I'm saying is when you do the dot product between the E field lines, the E field vectors, and the area vector, what you're measuring how parallel the E field vector is with the area vector, but that really means in the end that you're really measuring how perpendicular the E field is to the area. What I'm saying, and that's not to be confusing. It makes sense once you get it, and it's for a reason. But in other words, with 3 minutes left. Okay. With 2 minutes left. So this, I'm saying, I'm not trying to contradict myself or I'm not trying to confuse you, but this is confusing or can be until you get it. I'm saying in English, in the end of the day, what flux is amount of field lines going through an area, but literally going through the area. What we're trying to count when we count flux is we're looking at an area, seeing field lines that are going through it, but we're only trying to measure or count up or account for the components of the field lines that are actually busting through the area perpendicular to that area. The truth of the matter is that flux means flow. When we are counting flux or measuring flux, we are counting how much field line is flowing through an area, which literally means perpendicular. We're using a dot product, and dot products traditionally measure parallelism, but the thing that we're dotting are vectors that are already assigned to be perpendicular to that area. So there's like a two perpendiculars making a parallel kind of thing going on here. It's not meant to be annoying. It just is annoying. So I'm going to say it again. I'm saying if you were to look at a slab like your window on your car, and there were a bunch of field lines moving down the window of your car parallel to the window of your car, you could have a really big window of your car and you could have really a lot of electric field lines. But if they were all parallel to the window, then you would have big field strength times big area times the cosine of the angle between them. And because of the way we're defining things here, the cosine would end up being zero. You'd get no flux. If you have a bunch of field lines busting through the window perpendicular to the window, then every field line would count. You would do field line times area times cosine of the angle between them. The cosine would be 1. You'd have enormous flux. Anything in between, if the field lines were coming through at like a 45-degree angle, then you would do cosine of 45, which is like 0.71, right? So you would get like, so that you get like 71% of the flux that you otherwise would get. So I'm ultimately saying, and I know it's 420, I'm ultimately saying that flux is amount of field lines busting perpendicular through an area. That's what flux is, at least in the case when area is small. We'll pick up more on Wednesday about what to do when area is big, and it'll help more with homework. You could still do that homework that technically was due today. I'm sorry that it was, but whatever. You could, anyway. All right. So I'm here for any questions. You've been very patient. You're continuing to be very patient. I hope that's clear. I'm going to stop the recording, but if there's any questions, I'm here. Um, have a great evening.